All right, so now we're going to look at the order and convergence of multi-step methods. Okay, so we're going to consider multi-step methods in the following form. So there's some linear combination of the solutions and then on the right hand side is some weighted linear combination of the corresponding vector field values. Okay, and then n is going to go from 0 onwards. And you're going to assume that the AMs and BMs for m equals 0 to s are given constants. Which are independent of h. Which is the time step. Okay. And they're also independent of n. And the underlying differential equation. Okay, so to normalize this, we're going to require that a sub s is normalized to 1. So there's a normalization. Right, so a sub s is equal to 1. Okay, and as we saw, it's like with the Adams-Bashford and the Adams-Moulton methods, the method is either implicit or explicit, depending on whether or not there's a term involving the vector field evaluated at y n plus s. Okay, and of course that means that's related to this coefficient b sub s. Okay, so when b sub s is equal to 0, as is the case with the Adams-Moulton methods, so the Adams-Bashford methods, right, then the method is explicit. Otherwise, it is implicit. Okay. Okay, so the first thing we're going to try to look at is the order of accuracy of the method. Okay, so order of accuracy. And as we've seen before, one way to determine the order of accuracy is to look at the residual you get when you substitute the exact solution into the defining equation for the numerical method. Okay, so let's go ahead and do that. Okay, so I'm going to define phi of y and t. Okay, and so this is going to be defined to be basically, I'm going to take this and move it to the left-hand side, and I'm going to substitute the exact solution into that. Okay, so this is a sum from m equals to 0 to s of am y evaluated at t plus mh. Okay, minus h, the sum from m equals to 0 to s of Bm f evaluated at, well, I'm just going to write it, it's like in terms of y prime. Okay, so Bm y prime t plus mh. Okay. All right. So of course, if you had substituted the numerical solution instead, it's like this thing would vanish. But if you substitute the exact solution in general, we'll have some error. So it's going to be, so the leading order error term is big O of h to the p plus 1, at least in the asymptotic limit as h tends to 0. Okay, so if you have, it's like if you compute this and you find that the leading order error term is again big O of h to the p plus 1, then you say the method is of order p. Okay. So if this is true, and we want this to hold for all smooth functions, y, and there has to be at least one function where you actually achieve that error, right? So what that's basically trying to tell you is that you want to check that this estimate is sharp in order to say that the method is of order p. Okay, all right. So you might ask, well, how do you go about computing this systematically, and is there a sort of a nice, efficient way of doing this? Okay, and in service of this, we can introduce essentially two characteristic polynomials, which will turn out to be useful as we go along. Okay, so I'm just going to leave the general form of the linear multi-step method there. So I'm going to consider, rho of w, which is obtained by using the coefficients in this first term here. Okay, so sum m equals to 0 to s of am w to the m. And then I have a sigma of w, which is obtained by using the bm coefficients. Okay, sum m equals to 0 to s of bm w to the m. All right, so given these two polynomials, it's like then you can establish a result that's like having to do with the order of accuracy of the method. So this is theorem 2.1 in the book by Isserles. Okay, and I'm going to refer to this multi-step method here, right? So the multi-step method star, right, is of order p greater than or equal to 1 if and only if there exists some constant c, which is not 0, such that the following expression is true. Rho of w minus sigma of w natural log of w, right, is equal to c times w minus 1 to the p plus 1 plus something which is big O of norm of omega w minus 1 to the p plus 2 power in the limit as w tends to 1. Okay, so that's going to be the thing which we're going to have to prove. So let's see how you go about doing this. All right, so let's try to start with the proof of this. So you got to assume that that y is analytic. Okay, and its radius of convergence is greater than s times h. Okay, so essentially what I'm going to do now is I'm going to, so if you recall, it's like there's this phi, sorry, this is psi, it's like of y and t, right? And and what it is the defining equation for the multi-step method, but where you substitute the exact solution into this. Okay, so so what I'm going to do then is I'm going to replace it's like the solution of y at different times. It's like using the Taylor expansion for it. Okay, so this is the sum from m equals to 0 to s of am, right? And then there's a y at t plus mh term, if you recall. And I'm going to Taylor expand it about sort of the time t. So this is the sum from k equals to 0 to infinity. So it's just the infinite Taylor expansion, 1 over k factorial, the kth derivative of y, evaluated at time t. All right, and then there's the time step, right? So that's m times h, okay? So to the kth power, so that's m to the k, h to the k. So this is really nothing more than the Taylor expansion for y at t plus mh. Yeah. Okay, and then I'll do the same thing for the bm and the y prime terms. Okay, so minus h times the sum from m equals to 0 to s bm sum from k equals to 0 to infinity, right, of 1 over k factorial, okay, the kth plus first derivative of y, because I'm doing a Taylor expansion for y prime evaluated at t plus mh, and then m to the k, h to the k. So this here is nothing more than a Taylor expansion for y prime at t plus mh. All right, okay. So so let's now collect terms. Okay, so what I'm going to do is I'm going to collect terms in the same powers of h, right? So you'll see that there is one additional power h term, right? So the h to the 0 term just includes terms on the very first piece. So this is going to be the sum from m equals to 0 to s, right, of am. And this is going to involve y at time t. Okay, and then the remaining terms, it's like in higher powers of h will involve both the AMs and the BMs. Okay, so let's write that down. Plus sum from k equals to 1 to infinity of 1 over k factorial, sum from m equals 0 to s of m to the k am minus k, sum from m equals to 0 to s m to the k minus 1 bm h to the k, and then the kth derivative of y. Okay. All right. And so you've already, it's like written in the form. It's like where you have these powers of h. So as you might expect, if you want to get a method of very, very high order, then you have to get that these coefficients vanish, okay, to the appropriate order. So let's see how you go about doing that. So I'm just going to erase this part here for now. Okay, so you have this coefficient. Okay, so to obtain order p, right, what you need is the following, that this term vanishes, sum from m equals to 0 to s of am as equal to 0. Okay, and then these terms have to vanish as well. So sum from m equals to 0 to s of mk a to the m is equal to k sum from m equals to 0 to s of m to the k minus 1 bm. Okay, and this has to be true for k equals to 1 all the way up to p. And then in order for the method to actually have order p, it has to be that the big O of h to the p plus 2 term, right, the coefficient for that is not 0. So, so we have to impose that condition as well. And so finally, you want that the sum from m equals to 0 to s of m to the p plus 1 am is not equal to p plus 1, the sum from m equals to 0 to s of m to the p bm. All right, so this is just the same condition. It's like for k equals to p plus 1, it's like, but we want it not to be satisfied. And so this basically tells you that the error is actually, there's actually a non-trivial big O of h to the p plus 2 error term there. Okay, so so in principle, you could actually use these conditions, right, involving the AMs and the BMs to determine the order of accuracy of the method. Okay, so in principle, you could just stop here, but the statement of the theorem is that this condition, it's can be written perhaps more compactly in terms of these series expansions involving the natural log. So let's see how you go about doing that. Okay. All right. So so I introduce a new variable. So let w is equal to e to the z. Okay. Then what happens is that w tends to 1 as z tends to 0. Okay. So I'm going to write down, it's like this condition, okay, rho of e to the z minus z sigma e to the z, and see what you get. Okay. All right. So rho e to the z, by definition, is just the sum from m equals 0 to s of am e to mz, okay, minus z sum m equals 0 to s of bm e to the mc. All right, so now as before, it's like you can look at the Taylor expansions for these exponentials. So you get the sum from m equals 0 to s of am, and then I'm going to replace this with the Taylor expansion. So the sum from k equals 0 to infinity of 1 over k factorial m to the k z to the k, right, minus z sum m equals 0 to s bm sum k equals 0 to infinity 1 over k factorial m to the k z to the k. All right, okay. So now I can reorder, it's like those sums slightly. Okay, so this is the sum from, so I'm going to switch the order of the summation. So sum k equals 0 to infinity, right, 1 over k factorial multiplied into the sum from m equals 0 to s of m to the k a to the m. Okay, and then this is z to the k. Then minus the sum from k equals to 1 to infinity 1 over k minus 1 factorial. So here what I'm doing is I'm just reindexing the sum. Instead of going from k equals to 0 to infinity, I'm going to go from k equals to 1 to infinity, but every time I see a k, I replace it with a k minus 1. Okay, so that I still get the same terms. All right, and then that's the sum from m equals to 0 to s of m to the k minus 1 bm and then z to the k. All right. So so you can then check that these coefficients, if you will, give you what you need here. Okay, so these conditions, you can compare it with this condition here. So this tells you that you know, rho of e to the z minus z sigma e to the z, right, is equal to some constant times z to the p plus first power plus something which is big O of z to the p plus 2. Okay. And then this recovers the result you want. When you let w is equal to e to the z. Okay, so this means that z is the natural log of w. Okay, so this gives me rho of w minus big Z. So like Z is natural log of w. some constant, and what you do basically is that you write z, it's like the relationship between z and w, it's like in terms of the Taylor series, it's like for the natural log, okay? And then what this z to the p plus 1 power corresponds to is w minus 1 to the p plus 1, something which is big O of w minus 1 to the p plus 2 power. Okay, and so so again, it's like it just comes from this observation that the order conditions, it's like, can be written in this way, and you can rewrite it, it's like in terms of this particular expression by comparing the series for this, it's like with the order conditions which you need. Okay. All right. So I'm going to say a little bit about an alternative way of deriving these order conditions, and it comes from the observation that if you take this map from a function y to psi of t and y, which, if you recall, is this combination m equals 0 to s of am y of t plus mh minus h sum m equals 0 to s of bm y prime t plus mh. Okay, then this is a linear map. And so the condition that this is big O of h to the p plus 1, okay, is equivalent to saying that when you apply this map to a y, which is in the space of polynomials of degree up to p, right, that this thing is equal to 0 for such polynomials. So in particular, it's sufficient to check this for qk of the form t to the k, where k goes from 0 to p. All right, so let's see what happens when you do that. So psi of qk of t, and to make life simpler still, I'm going to let t be 0 here. Okay, so this looks like the sum from m equals 0 to s am, right? So this just becomes mh to the k power minus h, the sum from m equals 0 to s bm, and then y prime is of course just k t to the k minus 1, so I have k, and then the time is mh to the k minus 1. Okay, and want this to be equal to 0. And so this term, it's like has a common factor of h to the k in both of the terms. So this condition being 0 is equivalent to saying that the sum from m equals 0 to s of am m to the k power minus h. I'm sorry, there's no h here. Minus k sum from m equals 0 to s of bm m to the k minus 1 is equal to 0. All right, which is exactly the condition you have here. And then you can check that when k is actually equal to 0, right, that the condition just reduces to the sum of am being equal to 0. Okay, so in particular, if k is equal to 0, m to the 0th power is just 1, so this involves the sum of am terms. K is 0 means the second term vanishes, so the condition for the k equals to 0 case is exactly just that the sum of the ams equals to 0, which is the one here. All right, so that's just a quick way of deriving the same order condition as before. So let me just stop here.